We need to find the cutoff frequency for the FC high pass filter. Then we're going to look at different omegas and find the polar form for them. And then we're going to write the steady state output voltage for these. So looking at the following circuit diagram, we need to find the cutoff frequency for high pass. We've done one other problem similar to this, so it might look a little familiar, but all we have here is a capacitor that we need to convert to the S domain. It's going to be Z of C, and this is equal to 1 over S times RC. And then we have this resistor here, and then we have a V0 over it because it's in parallel. And so to start this off, we can start writing our H of S, but before we do that, I'm going to look at the F of C. This is what we need to find. Well, we know that omega is equal to 2 pi times frequency. And we need to find frequency, so we're going to rewrite this as F of C is equal to omega C divided by 2 pi. And so this is going to be the equation that we're going to use, and we need to now find our omega C. Well, we know that H of S is equal to V0 over Vi. We're going to use the voltage divider method. So we're going to have V0 is equal to Vin, and then we're going to have the resistor over V0, and this is 50 kiloohms. And then we're going to have that resistor plus the other impedance, which is 1 over S times C. Now, we can't have an S and a C in the denominator. We wouldn't want that. So what we're going to do, first we're going to multiply both sides by Vi. That way we can get it to look like H of S. And then we're going to also multiply this entire right side by S of C over S of C. And in doing this, we're going to get H of S is equal to 50K times SC. And this is divided by 50K times SC plus 1. So this is going to be our H of S. Now, again, we need to find our omega C. To find our omega C, we can look at the notes linked below the like button. We are going to be looking at this. We have omega C is equal to 1 over RC. So in here, we can write omega C is equal to 1 over the RC. And our RC is going to be this. This is our resistor, and this is our capacitor. So we're going to have 50K times the capacitor. We can now write the capacitor in. We know it's 5 times 10 to the negative 9th because that's nanofarads. And this is going to give us an omega C of approximately 4,000. So this is our omega C. We are now going to plug this into here. We are going to get approximately 637 hertz. So that is the frequency here. And that was for part A. Now we can look at part B. And in part B, we need to find our H j omega. So what we can do is write out a general equation and then plug these different scenarios in. We have H j omega, and it's equal to, we're going to use this equation and replace the S's with our j omega. We can also replace what we underlined in red with our omega C. Now, I'm going to change this to green. So this and this can be replaced with this. If we rewrite this as 50K, we know that this is just our capacitor. So we have the capacitor is equal to 1 over omega C. So keeping that in mind, let's rewrite this. We have 50K times our C, which is the capacitor, times our j omega. And this is divided by our 1 over omega C. And that will replace everything that we underline in green, times our S, which is now j omega, plus 1. Now, the different scenarios that we're going to have are, first, when H is our omega C, and our omega C is 4,000. And then also, when we have H as 0.2 times 4,000. And then the third scenario, where we have H is 5 times 4,000. So the first one, we're going to go into Symbol Lab, and we're going to plug everything in. What I have in parentheses is 4,000 and this 4,000. We are going to change it based on the scenarios. But for the first one, it's 4,000. So this is going to give us a 1/2 plus j over 1/2. And that's this right here. This is the rectangular form. We need to convert this to the polar form. So the polar form is where we get the magnitude. And this is going to be the square root of our real number squared plus our imaginary number squared. And then we have the angle is equal to the tangent -1 of our imaginary over our real number. And in doing this, we're going to get approximately 0.71 at an angle of 45 degrees. And now we can look at the second one. So we're just going to go back into Symbol Lab. We have our omega c, but now we have it being multiplied by our 0.2. So we're going to multiply this by 0.2, and then come in the denominator and multiply this by 0.2. We'll press go, it'll calculate, and it's going to give us a 1 over 26 plus j times 5 divided by 26. And now we need to put this in the polar form. And from this, in our polar form, we're going to get approximately 0.20 at an angle of 79 degrees. We're going to come back to our matrix calculator, or imaginary number calculator, and we're going to multiply this by 5 instead of 0.2, and this by 5 instead of 0.2. Press go, it's going to calculate it for us, and then we're going to get 25 over 6 plus j times 5 over 26. And so we're going to get 0.98 at an angle of approximately 11.31 degrees. Now, looking at part C, if we have our V input T equal to 500 times cosine omega T millivolts, we need to write the steady state output voltage V naught T for all of these. Well, it's important that they mention steady state. If it's steady state, our omega is going to be the same. We can see that we just have an omega here and a simple omega down here. Now, all of this right here correlates to what we have right here. And so our angles aren't going to change. We're going to have 45 degrees here, 79 degrees here, and then 11.31 degrees in here. The only thing that's changing is the magnitude, and that's because we have this 500 out here. And so we are going to need to multiply our previous answers by 500. And that's going to give us 355. We're going to have a 100, and lastly, a 490. So that's how you would go about looking at this kind of problem or something like this. You just follow those steps.